Okay, so it's 2 o'clock, so let's get started. So today our speaker is Wenbin, as a co-PI of a NASA Drive Center project. Wenbin is leading a team at HAO developing a whole geospace model. He will talk about this model today. Here is a short bio of Wenbin. Dr. Wenbin Wang got his bachelor's degree in physics from the Nankai University in China, PhD in atmospheric and space sciences from University of Michigan, and a postdoc at the University of Michigan. He has been a project scientist at NCAR HAO since 2000. His research interest includes the development of high-resolution models of the upper atmosphere and coupled whole geospace models to study mesoscale processes and cross-scale coupling in the thermosphere and ionosphere system, and the response of this system to varying driving solar wind conditions. His current research interest includes ion-neutral coupling in the ionosphere and the thermosphere system, thermosphere and ionosphere responses to geomagnetic storms, and the effect of the lower atmospheric waves on the thermosphere and ionosphere. So Wenbin, please take over.
Yeah, thanks, Lin. Thank you for the invitation. So today, I'm going to talk about some mesoscale processes in the thermosphere ionosphere use simulated by recently developed high-resolution coupled whole geospace model. So the goal is to resolve those mesoscale structures that are not well represented or simulated by the current models. And so I really acknowledge most work done is here is by Dongling and Kevin Pham here, and also I thanks Slava working as the PI of Center for Geospace Storms, which is NASA Drive Center, one of NASA Drive Centers, and the model development team on the CGS, and also clearly many colleagues inside HAO and outside the HAO. So when we talk about the mesoscale structures, what are they? How they defined? Clearly, they're not unique or well-defined. Since talking about well-defined signatures of mesoscale structures. So this is just a very rough classification, but also the mesoscale structures depends on how you observe it, where you observe it, when you observe it, and also what the characteristic scale or length you try to define, because some structure can be very narrow in, say, longitude or latitude, and very long in magnetic local time or longitude. So it depends on how you define it. But anyway, so here I just based on some very rough estimation for the large scale is in the upper atmosphere processes, mostly it's 5,000 or 10,000 kilometers wide. We talk about tides, global planetary waves, neutral wind general circulation, and large scale geomagnetic storm effects. Those are can be resolved by current global circulation models with proper specification, because thermosphere system clearly is an open system, not an isolated system. So it's being affected by bottom and from above. So you need external force, and if you have the right external force and with, then we can properly resolve those large-scale structures. However, the mesoscale structure, which I would say from 20 to 30 kilometers to 1,000 kilometers or 2,000 kilometers, those including, which I will cover a little bit, like mid-latitude density trough, bubbles, equatorial plasma bubbles, and traveling TID, traveling atmospheric disturbances. In the high latitude, you have polar cap patches, ton of ionization, geoheating, boundary block, those things and also subauroral polarization stream. They are in one way, one dimension, many dimensions. They are subauroral mesoscales from 330 kilometers to 1,000 kilometers. So I was most working use example of polar cap patches and TAD and SAPS as example to see how we simulate those with whole geospace model. So our goal for CTS or for whatever, with my one sentence summary is we can resolve those mesoscale processes. Here is focus on IT system, but the whole geospace, a lot of mesoscale because they're cosmic scale coupling with high resolution model and also with the physics still valid within this domain. Okay, so this is a rough definition of whole geospace, the mesoscale structures. So first, give you an example at high latitudes, which we talk about is the stormy has density, which around here. Here, then when it's evolving put into polar cap, it's called TY, ton of ionization. Then it's segregated into polar cap patches. Those are the small mesoscale structures and the subauroral polarization streams, SAPS, within the mid-latitude density swap, electron density swap, and polar cap holes, boundary blob here, all those electron, all those are within the on top of the background, the positive storm effects here, and negative storm effects can be global or can be mesoscale. So all those are defined space weather in the IT system, especially for those, you can see the sharp edge of those structures which produce plasma instabilities and also scintillation, so have strong, very significant space weather applications. So also with those structures, we can see small mesoscale structure in geoheating driver waves. One of the waves is traveling atmosphere disturbances, which for this one is generated by geoheating at high latitudes with temperature changes and then enhance and then produce waves. Large scale waves, also mesoscale waves, propagating from high latitudes towards lower latitudes, which I will give more examples of those things. This is also one example, is the high latitude driving or for Magnetosphere driving, but also those TADs can also drive from a lower atmosphere, from tides, from mostly gravity waves, drive mesoscales. So that's another type of TADs we want to study. For another one, the mesoscale structures is we call the SAPS. So subauroral just define what is SAPS. This is electron precipitation. Here define the high latitude auroral part, then subauroral, based on electron precipitation, where the ion precipitation can sometimes, the most occur in the subauroral here, just equivalent of the auroral electron precipitation. Then you have really westward or sunward on the dusk side, high speed ion plasma strips, ion strips, which we call the subauroral polarization streams. So this is a DMSP observation. If you look at globally, this is a good way, give you aurora. Then this is the SAPS. This is the regular high latitude return flow. So then here gives a Schubert observation, westward flow like this, or sunward flow. So I'll give you three examples of mesoscale structures. So how we deal with it, how we simulate it. That's the whole talk about this one. Before doing that, let's say, as I said, the thermal ionosphere is an open system. It's affected by the inputs, energy inputs from the Magnetosphere. This is a microdata paper on this called the birthday bulk flow. When you have storms, you see those channels or flow channels moved earthward. Then it's build up the recurrent, produce density gradient, pressure gradient, then drive partial recurrent, and then reason to current or the field line current. Then associated with geoheating electric fields, everything there, so affect the high latitudes and then the nonlinear system response. And the low latitude, this is a Chinese work. We use vacuum. You can see it's a lot of gravity waves concentric gravity waves or other types of different scales of gravity waves propagate upward to the IT domain, where they can generate, affect the electric field, generate the TADs, another type of TADs, and also affect the generation, propagation of plasma bubbles. So the IT system responds to both forces from above, from below, and also it have internal dynamics, linear and neutral complex. So it's really a complex system. To fully understand the processes of different scales, including mesoscales, you have to treat the entire geospace as one system. So that's why we want to develop whole geospatial model from ground all the way up, and take a solar wind conditions from every point of. Ideally, we want to also from the core of the sun to core of the earth, but that's too big. We can't do it with current capability of computing or physics. So we're just starting from the every point to the geospace right now. So the first generation of our model is called a MATE, multi-scale atmosphere geospace environment model. We have the version is 1.0, which we cover the core area, models of core area. One is the Camera, which deal with global Magnetosphere MSD simulation. So what is take solar wind, dealing with solar wind, the Magnetosphere or Earth magnetic field interaction, dealing with tail dynamics, and as I said, like the Mach data, burst flow. Then we have the recurrent model called the rise convection model, dealing in the Magnetosphere, recurrent. Then we through the ionosphere electron coupler, coupled with TIAGCM, which all are two-way. So like the precipitation from RCM and the mirror can pass through to the TIAGCM, calculate the conductance, affect the wind, then this feedback to this remix potential solver to get the electric field from we also use a field like current from Camera and RCM to solve the electric field. And then this electric field being transmitted to all the components, models to affect plasma distribution and motion. So currently we have this model is we call 1.0 already developed, and it's now in full production. Okay, we are writing papers based on this model. So the current highest resolution, as I said, if we want to do mesoscale simulation, we need high resolution. So here is the 0.625 TIAGCM and 0.25 in the Magnetosphere domain. So this maybe we should say first really adequate or high enough model to deal with the whole geospace mesoscale process or structure modeling. Okay, so this is the background. Now let's give you the first is the SAD, TY, and the patches. So when is the people talking about those kind of enhance the density that normally talking about storm case, but Jing Liu was here in HAO back a few years and to demonstrate that weak geomagnetic activity can also drive those mesoscale structures. And it's all depends on where the convection pattern, this is a superdark convection pattern, located relative to the ionization source. So if you have the right source and the right location, then you have the path is or TY form, the SED form. So those are actually all not always occur, but it can occur all the time. So regardless of your physical conditions or geomagnetic conditions, but it's the occurrence clearly depends on location of the convection pattern and the UT and everything. So this gives you just an example of this. So here, one of the things that people still debating is where those plasma comes from. For the SED, you can see this is the difference from quiet time. You see the electron density enhanced for two storms in sympathetic storms. So this actually is clearly is caused by plasma transport. However, it's just a horizontal or vertical drift. So Jing's work later on found that you can see here is E equals B horizontal transport, whereas E equals B vertical, basically from the lower F region to the top side F region. You can find actually the horizontal transport is not actually deplete the region of the new sector. So it's not the cause of the production or the formation of SCD. But however, horizontal direction is the transport effect to cause the TUI to transport into polar region. So this is give you the horizontal view. If you look at the vertical line, so here is the lower latitude from 60 for the mid latitude. This is the difference again. So this is the SCD part. So here is the high latitude part, which the problem is the TOI. So what we see here, actually, this is a diagnostic analysis chemistry, not important here. It's the most important is the wind transport, which is a push the plasma up and down related to the magnetic field lines. And another clear is the total transport of plasma, however, by the electric field equals strips. However, in the lower or in the middle latitude, the SCD region, it is not the horizontal transport is not a cause of SCD, but the vertical drift, which is boost plasma from lower latitude to higher latitudes, higher altitude. Whereas inside the polar cap, say in the 70, 80, for the TY, you can say horizontal transport is important for the formation of TY. So this gave you the standard low TIGCM simulation results with cost grade. I believe this is 2.5 degrees of simulation. Now I present you with fully coupled maze 1.0 with 0.625 simulation results done by Kevin. No, the first one is also, forget this slides. Basically talking about the TY occurrence clearly depends on the UT, where if you're close to the region of positive storm effects, close to this, you drag a lot of plasma into this, you have stored TY. Whereas if your convection pattern is away from source region, then you don't have much to propose in. So then you have a weak TY. So this is critical depends where the convection pattern relative to the daytime polar solar produced ionization. So this is basically demonstrate that those TY or patches form strongly depends on the UT and also clearly MF BY components, BZ components. So okay, so let's move on with the what we have with the Maze 1.0 high resolution simulation. So this is the August 24, 2005 storm. So you have a BZ really minus 50. So although the DST is about 170 or 150. So here the actually storm, this is the source of driving at the 6 UT. Then the main phase about 10 to 12 UT. Then this recover phase. So first I give you a stance still with when is 12 here. So you can see the convection pattern is in this peak is dragging the plasma into here to form those patches here. And later on, when the 23 UT or 21 UT, so the convection pattern is here. So it's you can see it's a double TI here form. When it's dragging the plasma from afternoon sector, when it's dragging push the plasma to move in the early morning sector. So you have a double TI occurring. So now let me not play the movie, but drag the movie so that save a little bit time. So the first before 6, we do it's a quiet time, so-called quiet time. But you can see, as I say in Genius research, it's a quiet time. You still have those TI. Let me show you. So if you drag, you can see here. You see the plasma moving here. Also, you can see the patches form here and then moving into inside the polar cap region. Even in quiet time before 6 UT, So that's a very important. This kind of process actually is it's happening all the time. Let me drag further. Then into when the storm occur at 6 UT, so you say it's a convection pattern mostly located in the afternoon sector. You see a lot of TY form from the SED region, then into the pole, into the polar cap, and a lot of significant patches as well as TY occurring, and just a really complicated system. We haven't really work on so how this happening, why is this happening. But anyway, so here you can see the convection pattern, the negative storm effects happening. So this is a low density region, so you have to, plasma has to be dragged all the way from here to here. So with a very long, elongated TI, and then it's patches formed here. So let's move on, continue as storm progresses. So you see the constant structure occurring here. Then is we see still here. Lower the northern hemisphere is not as dramatic as the southern hemisphere, but here we have a little bit of precipitation. So now move to here. The convection here is away from daytime ionization rate. So there's another source of TI can happen. You can demonstrate here, which is a form of precipitation. You can see here. Now here, look at here. So these are the produced by precipitation, but dragged by the convection pattern into the inside polar cap region. Then after in later UT, when the convection pattern merges or the cut into dayside precipitation, then you have two kind of channel occur. One is dragging plasma from nighttime, from afternoon, another is from noon, and form really very complicated structures inside the polar cap. Those are the things that we're talking about. We try to simulate. There's clearly a lot of things that still need to be studied for this one. The outstanding issue like those patches, how they formed, why they formed, how they dissipated, and also the how if those patches can affect the outflow, like O+ outflow, polar wind, and also in this kind of localized region, most likely strong geoheating will happening. So today that generate waves propagating towards the low latitudes. So all those things we leave for us to study and to work on. So related to geoheating generate, so now I move to the same storm, but just a look at a different sector, which is the neutral density perturbation at 400 kilometers with the satellite chamber height, which we have data to compare with. So the first thing, as I said, even during quiet time, so-called quiet time, you still see that this is use a fixed scale, so maybe not very clear. You can still see waves, large scale, measure scale being generated at high latitude, propagating towards the low latitudes. So you can see those waves, but at 7 o'clock, so you can now 6 o'clock, what we see is a storm geoheating produced here. Then you see the density perturbation of different scale, large scale and small scale occurring. Then it's a move forward. We say you can see those stress and the propagating towards the lower latitudes. But the interesting stuff is we do see those kind of large scale with the what's called large scale TID. Embedded on that is the massive scale structures of density perturbations, which I believe is the main is the maybe not the first model, but the model can resolve those kind of massive scale density perturbations. So let's move on. So as storm may phase occur, you can say strong depletion, and with also different scales kind of waves on neutral density perturbation generated, and it's large scale waves propagating towards the low latitudes, and you see different regions of the TADs being generated at different regions. So just to show you what it looks like, how dynamic it is. So another thing to look here, specifically at this 12, so you have two large-scale waves embedded with mesoscale structures propagating towards the lower latitudes and collide together. So you can see that the form interference, constructing interference, actually produce large, very large density perturbations here. Then it's moved to other places. So this is what we see at 400 kilometers during the storm. Same with maze. Another thing is you can see those waves not just propagating equatorward, also poleward towards. So it's probably produced both ways, probably at daytime or region or whatever region. Then it's propagating both ways. So and also of different scales. So this is just and that is play again, so you can feel how dynamic it is. This is in the recovery phase. You still see a lot of waves in the say southern hemisphere, as well as northern hemisphere, generated and propagating towards lower latitudes and also high latitudes. So those are the things we see in the movie and in the maze output. Let's go give you a detailed analysis of how we compare with the model. So here is the grace. It's about 500 kilometer water height density. This is Chairman, 400 kilometer. The black line is the observed density. The red line is the maze output. The blue line is the Weimar drive standalone TIEG cell. So overall, you can see that the maze doing a lot better than the Weimar, especially in the storm and early recovery phase. It looks like Weimar's overestimated density response, whereas maze looks right on target, especially doing much better in the recovery phase. So let me focus on two times. One is 7 UT, and the other is there's two peaks. This is in the initial phase. This is in the main phase, or just in the early phase to look at what is happening. This is, I believe, the model is reproduced density gap where that's happening. So at the 7 UT, which is in the initial phase, Chairman, and I just roughly put the locations. Where is this is the polar south region? So the Chairman and Grace simulate densities near the daytime, near the cusp region, in that region. So this is whereas at the 13 UT, when this one happening, large density peak, which is actually so occur when the two TADs collide in the, this is at 11, this is the 12. So you can see they interact in the equatorial region, produce a large density peak that's what's being captured by Chairman and Grace, also simulated by the model. So this I really like this plot demonstrated. What I want to see is the large scale, not just the simulated large scale TADs with most standard synchronism models can do. Also those mesoscale structure density perturbations, which I believe I don't have time, but we say the Cham also those kind of observations. So basically, we can see a full scale of different temporal and spatial scale density perturbations being simulated by the maze. So this why we do that is because why maze can do better than the empirical Weimar model is because it's geoheating. So this is simulated. This is at 7 UT, where geoheating, you can say, with very smooth, as you is almost captured by the Weimar, but it's very smooth. However, at 10 UT, you can see the major simulated kind of very sporadic, localized geoheating, which generate both mesoscale, small scale, and large scale TADs, whereas Cham is just a very uniform, globalized, large scale geoheating pattern. So clearly, those are the different color scales tell you different things. So this here is the hemisphere, integrated hemisphere power, the geohelium. So kind of geohelium is VOS made by Weimer during the May storm, storm May phase, but also the location may be other, the right location to capture, to generate the waves, TADs being simulated or observed at the low and the middle latitudes. So this is further to demonstrate. So those large-scale waves propagating towards the lower latitudes, when you view as a fixed longitude, so time evolving, so you see the waves propagating from high to lower latitudes, and also those small-scale waves also generated, but they not normally they just stop at about 30 degrees, not propagating all the way to the lower latitudes as large-scale waves. Another thing I want to point out is clearly there are hemisphere asymmetry in those wave structures, TADs. Don't have time to go through this, but very interesting and a lot of studies needed to fully cover. So another thing, what I want to talk about is SAPs. So this I showed this before. So we see the SAPs channel here, and it's observed. So we just say model, how the model simulate this one. So the SAPs occur due to from the magnetosphere. That's why we need a full whole geosphere model, because the driving force for SAPs is the magnetosphere. When like I showed earlier in the Mike's paper, there's a birthday bulk flow moving from a tail to towards the earthward, and then produce plasma. Then they build up and the pressure. So those with a partial recount build up, whatever, then generate region to count in this region, which is downward in the dusk, on the dusk side. And this is region 1, this is region 2. Downward region to count has to be closed here through the ionosphere and back. So to make a count circuit. So what happened here when you have downward region to count? Here, actually, I didn't have time to talk about, but you have a very low conducting region called Mid-Latitude Swap. When you pass through the low conducting region to satisfy current continuity, so you have to have a huge build up a large poleward electric field. Then there's a then current to flow back to the magnetosphere through region 1. So here is where the SAPs occur. So in the subaurora dusk side, and this is the current flow this way. Now you have a storm poleward electric field drive southernward flow or westward flow, storm west flow. I just show the previous image here. Okay, so this is kind of is the SAPs mechanism, but to fully simulate this whole system, clearly need a whole geospace model, ionosphere, thermosphere, and magnetosphere coupling within the magnetosphere recombinant model. That's how the maze can do it. So this the first thing is we clearly, as we said, subaurora electron precipitation is very important. So in this in the maze 1, we actually implement diffuse electron precipitation. Those with from RCM, with including drift physics. So this is the so we combine the model precipitation from MSD and diffuse aurora. This is done by Dongling. So here HAO. So then combine with diffuse aurora to make a full diffuse energy electron precipitation pattern in the high latitudes, and then the subaurora region is here, where SAPs occur on the dusk side. So with this one, with the new tools, with the new model, how we can, if we can better simulate SAPs. So yes, actually is so. This is the energy flux precipitation. So when this message here is this is identified the boundary between subaurora electron precipitation. So here is DMSP I believe it's 18 or 17. Anyway, so observe 18 observations. So you see there's SEPs. This is subaurora, then there's another peak. So the model simulated this two peak structure. I believe this is the first whole geospace model can actually simulate this kind of two peak structure. I may be wrong, but I just so this is the non-hemisphere path for DMST 18. Here is the southern hemisphere path, so go this way. So you have subaurora cut, or observation cut. So here you have the SEP simulated, and right, looks like the model overestimated the SEPs, but with clearly we say the same location, subaurora, we say strong drift, which is similar situation here also southern hemisphere path. So you can see subaurora, you have SEPs, here's the observation. So I would say, I won't say quantitatively, but qualitatively, I believe the maze clearly simulate the SEPs structure, two peak structure with very distinct kind of flow channels of SEPs. So here, related to the mechanism for this one, clearly we have the upward drift, upward or downward drift in the region 2, which is where the SEPs occur. Clearly, I mean, so we just qualitatively can simulate SEP structure, but quantitatively we're still far away from fully reproduced observation. Also, clearly, this is a recount from the DMSV, so it's a lot of small structures, but the model is still, even with the resolution we have, but still very smooth and cannot capture all those variabilities, which that's our goal, our stress, to really capture all those kind of different structures, signals. But this is the first step, I believe, reasonably happy with what we have now for the SEP simulation as well as the whole space simulation. So here is to give you how the SEPs vary with solar wind conditions. When it's at the beginning, solar wind is northward, so you don't have much to see. As this is a westward drift, you don't see clear SEPs channel, and the field line count is weak, and then almost no precipitation. In the storm initial phase, what we say is the field line count is built up. You have region 2, region 1, and associated with that precipitation. So you do see the SEPs channel. The magenta line define the subaurora, and this one is defined as region 2 count. So this between here is the SEPs channel, as I indicated before. So this one is the SEPs channel. You actually SEPs occur firstly on the dust side in the about 18 to 20 MLT. Then when you have a full in the May phase, region 2 is fully developed. Then you can see SEPs channel always heading towards the midnight. This actually is consistent with the observation. SEPs first occur on the dust side, and then extended all the way to the midnight. And then in the recover, there's a period of BJ southward, the magnetosphere is reconfigured. Then the SEPs is a little bit, you have a SEPs channel here or there, but not as evident as in the storm May phase. Okay, so as alluded, so the diffuse aurora is really important for this one, for the SEPs formation. So here, down data and test with one with the diffuse aurora included, one is the result. Whether you see the result of diffuse aurora, actually the entire system response. So you have different magnetosphere and this counter system also differently indicate the nonlinear feedback effects. But anyway, so when we have the diffuse aurora, so you have this is the well-defined SEPs of the drifts. Here is the region 2 current, upward region 2 current, where SEPs occur. This is the diffuse aurora mono high latitude aurora per one. So this is with diffuse aurora. Without diffuse aurora, you just have very broad peak. This is 20 magnetic time. You don't see much define the two peak SAPs. The SAPs is all the flow channels move to higher latitudes with that's a typical, I believe, with our early CIMMYT model. That's what happened here, although it's not to this extreme. Okay, anyway, so another study, recent study data was we studied the data study for the MF-BY dependence. When you have this is a very good case for EZ dominate, and then you have a negative positive EZ, roughly same magnitude with the VZ. Then you have a pure positive BY dominant case. So the manosphere is reconfigured. Here in the BZ dominant case, you have a birthday bulk flow BBF, whose density build up recurrent. Then when you have a long with the BY roughly equals BZ, then the plus the manosphere reconfigured and asymmetric. For BY dominant case, clearly it's even more to the rotation, westward rotation, rotate towards day side. So this is reflected in the comparison with the fuel line count. So this also at the 3 time scale. So this is the major output, the region 2 current, region 1. This is the APM output, region observations. So I reasonably well produced. In the main phase, you have this is actually color scale is offside. So this is also downward region 2, upward region 2, upward region 1 here. Then you can reach the BY play rule. Then the whole pattern rotate toward day side. And more so when BY dominated went to the manosphere reconfigure, and then to here where there's a BY dominated for a long time, then you have really different structures as the manosphere. So now we look at what we have observed or simulated. For the first one is BZ dominated or the initial phase or whatever. So you have a very broad division. The peaks, suborbital drifts or SAPs merge with the main return flow in both. This is the 18 local time here, MLT. This is 17 MLT here. You do see a broad peak, both including both return flow, high latitudes, as well as the SAPS region. Here, in when the BZ is smaller than 0 with the second time, so you have a very large peak in 17 MLT and 16 MLT, so very small peak, which captured reasonably well by this is the one peak, this is the suborbital peak, which is SAPS being captured by model in the structure-wise, not quantitatively, not quantitatively, but we see that also you can see it's rotated towards the day side. Here is more so in the BY dominant case, you can see the with the current rotated towards the day side, towards the new. So you have SAPS clearly in the, this is 15 local time, this is 16. In 16, you see a broad peak here, around here, and then in the 15, you see actually very distinct peak. So the model captures kind of those SAPS variability with MF-BY and with the solar wind condition here in the later stage. So the SAPS channel is actually merged with the main flow. You do not distinguishable. So all in all, we can see SAPS drift toward day side when the MF rotate from southward to eastward, and isolated SAPS channel emerge during this rotation and merge with our convection pattern. So I won't say reproduce, but clearly it's a capture kind of this SAPS response to solar wind changes, especially MF-BY. So far, what I present here is what we do. We have a newly developed high-resolution MATE 1.0 whole geospace model. We can do, since I gave you 3 examples, we can, with this model, we can also do a lot of things, like those questions, how does the magnetic force and drive traveling ionosphere? So I show you something of TAD, but there are a lot, especially the correlation between TAD and TID. It's a worth study. And also, I said geohelium produced this, but where, at which altitude, when it's produced, is still, to me, it's still a mystery. We need but we use this model and do some study on this one. And also, I show the next storm effects, positive storm effects. That's sometimes you do have ionization source, you don't. So that's regulate the occurrence of SED, occurrence of TOI, those mesoscale structures, highlighted mesoscale structures. And so how those processes are happening whatsoever, we still not fully studied or fully understood yet. Then also, I show you the strength and grace density preservations globally, which I believe is associated with TADs, but still much work needs done of different scales, the propagation speed, daytime, nighttime difference. A lot of things can be studied with this model. Also, this model does not have cost precipitation yet, so that's another thing we need to work on to add those things to say how the cost. There are some peaks, density peak in stream of grace not being captured by the major model, which I didn't show, but anyway, so those I believe in the cost region, so we need to work on that. So another thing that other topics that we don't really, I don't have time to talk about is the how the wind circulation or conductivity feedback to the MIT system, how it's affecting coupling, also the like neutral wind flywheel effect, all those things that we can use MATE 1.0 to study. Recent studies, I believe transient solar event like flares and eclipse, which we can do this. Recent we had 2 tests. Solar flare, which clearly happened at the high latitude polar region, changes conductivity that can affect the MI to some extent, but we don't know the geospace coupling because your conductivity gradients change and that affect the coupling between the magnetosphere and the thermosphere. But anyway, with all those capabilities enabled by the measurement, there's still a lot of mesoscale structures are not able to simulate by this, especially for the IT perspective, is the low atmosphere coupling. So then, so our goal with the CGS, if we're lucky to get phase 2, so we want to have a much more complicated coupling. So I said those dotted lines is what we have right now. I present you now. So with full MATE, we'll have a multi-fluid camera, and also with the first thing is IPWM, which simulated O-class outflow from the ionosphere and polar wind, so affect the storm dynamics, and that's one of the things we want to develop and to have the capability to do that. Those are also related to the if like a TOI or patches affect the MI coupling through the mass coupling part. Also, we would like to have global electric solver. Right now, we solve separately, but we want to seamlessly solve a global solver electrodynamics or ionosphere electric field, so that we can simulate the penetrating electric field and the dynamo and everything. So there's a whole global electric field. So that's very important for our study. Then we also couple with the chemistry. So that's give you another lead is the plasma bubble occurrence and other things. With all that, we all need one model is the vacuum X. So we can show you Chinese model for simulation for waves, got different kinds of waves, planet waves, tides, and planet waves, gravity waves. All those waves propagate upward, affect IT. So how those coupled to the entire whole geospace is a topic for study, and we don't have that capability yet. So that's what we want to study. So that's what we want to develop with really high res. We can resolve most of the gravity waves or some of the gravity waves, and the tides and gravity waves to see their effects on the IT system during both storm time and not storm times. Okay, if we have this is just my personal view of what we can do if we have that full image, high resolution, fully covered image. Just those questions is only related to logarithms of coupling. So I just read them and then I stop here. First is I saw TAD and TIDs can be generated both by high latitude inputs and also by low atmosphere gravity waves. All those kind of things during the storm time or even quiet time, how they interact with each other, shape those thermospheric response in the mesoscale, the mesoscale, TADs, TIDs. Then another one is the global circulation. Circulation and local cycles in different layers of the atmosphere. So basically, it's how deep the manosphere influence, geoheating, whatever, can affect some atmosphere. It can down to mesosphere or stratosphere, especially through energetic particle precipitation, through chemistry, through dynamics. So those are the previously people just use parameterized kind of input, but we want to dynamic simulation, the fully evolution of this precipitation, as I just alluded before. Then also the low atmosphere waves, how they precondition the geospace effects like mixing, lower atmosphere circulation, all those, and also like we have gravity waves different in the sun and non-atmosphere, how they can introduce a symmetric response for the storms, and those are the questions we want to understand. And also what are the, this is a big question, is plasma bubbles. How does the low atmosphere waves and the high latitude penetrating electric field, the disturbance dynamo affect the generation, development, and the dissipation of plasma bubbles, like the propagating, when they can be enhanced, when they are suppressed, and they propagating westward or eastward as compared to gold, satellite emission gold, the local observed a lot bubbles. So I believe with this fully coupled major model, we have a can move much further in not, I won't say forecast, but in understand current bubble signature structure and their development. Also, there's another pending on questions that we don't have even guess if those like the possible low altitude waves like tides and graduates at the lower latitudes, high latitudes, polar region, if they can, when they propagate, affect the conductivity, if they can do, then affect the mass circulation like O+ outflow or through modified conductance, then affect the geospace coupling. So that's the questions probably we can address with this fully developed coupled with vacuum max, which will be our next step if we were funded and we have the manpower to move forward with that effort. But we believe we can move. It's really exciting to move forward with. We can address all. So this is just my kind of thought, but I believe audience and a lot of people may find all other things. A lot of possibilities will be open with this whole geosurface coupling from ground above, taking solar wind, solar influence. So that's just, I believe, looks the future is pretty bright with this whole geospace modeling. With that, I would stop here and take any questions. Thank you.
Thanks, Wenbin. Ling had to leave early, so she asked if I could help handle the questions. So if anyone has any questions, you can either type in the chat or speak up. Ling did have a question that I can read that you put in the chat. So the slide of mass density model data comparison shows that the MAGE model can simulate mass density during storm recovery phase very well, whereas the TIE GCM with Weimer greatly overestimates mass density during the recovery phase. Since the TIE GCM is also the TI model in MAGE, she thinks that this sheds light on the reason of the issue with the TIE GCM being too slow in recovering after storms. It suggests that the slow recovery was not because of NO cooling, but inaccurate solar wind forcing.
What I'm look at here is actually, there's a probably talking about here. I believe it's still, as I said, probably the manosphere forcing still off with geoheating, popping whatever. Also the location where geoheating happening in the recovery phase. So looks like NO cooling from here, maybe as indicated. I haven't thought about that yet, but it looks like it is a manosphere force and maybe more important, but we need to take a further look at it. So yeah, that's a good question. Actually, maybe a future study to really to understand if in the recovery phase actually with this kind of a model simulation looks like the more manosphere force. But yeah, we probably need to do more study on this front.
Okay, are there any other questions?
I'll just add an addendum to this comment by Li Ying and Wenbin's response. Another possibility is that what's being shown in this figure, I think, is the orbit average density along the satellite trajectories. And so it's not just the solar wind forcing, although that may be a major factor, as Li Ying points out, but it could also be that the distribution of enhanced density at these satellite altitudes along their orbit tracks is quite different from the density along track that MAGE is producing. And so, it could well be the distribution is what's affecting the comparisons of along track densities here.
Yeah, this is a long track. I don't think Kevin can say more. I don't think it's the orbit averaged.
It's orbit average, yeah. So you can't really say a whole lot without digging into it. Yeah.
These are not the orbit averages.
It's
these
not
are
orbit averaged.
Oh, these are instantaneous values.
Yes, that's why we say the TAD. I saw the plot like here. That's where it's density being observed and the density peak being simulated. So it's not non-orbit, but it's at the instantaneous location.
Yeah, but the issue still remains that the difference between Weimer and MAGE may be the distribution itself of density along the orbit track, regardless of whether it's orbit average or instantaneous. So that anyway, that's
yeah. I would like to see a movie with Chapman Grace on compared to the Weimer driving. Is those large scale waves are different, are the same? Are they the TAD being generated at the same location or different location? Considering geoheating pattern can be different, so it would be very interesting to look at when in the empirical Weimer case, where and when the TAD being generated as compared to in the MAGE. So that would answer or address, I believe, part of your question.
Yes, thank you.
Yeah. Oh, that's actually I don't want to call Kevin to a quick study, but it would be very interesting to look at. Yeah.
Sounds like another paper.
Oh yeah, a lot of work to do. Yeah. Okay.
I also had a question earlier on in your talk when you were talking about the TIDs or not TIDs, the tongues and formation of patches. Yeah, and it was one of the global patterns, and there were some what looked like very unusual patterns in NMF2. Not in this one.
This plot.
Well, it could have shown up in late in the animations that you were showing, I think.
I know.
Yeah, right. Like if you drag your cursor out maybe 3/4 of the way, but there are some really unusual, like right here, some really unusual structures. Do you know if there's any evidence for those things in data? I mean, observations may miss them, but it just seems unusual to me.
Yeah, actually, one thing is I don't know if here we have evidence for that, but here, especially later on, there's development that's really cut off just after sunset. There's people being talking about the extended bubbles or whatever. So we do seem to be that there's a dusk density depletion from the equator all the way up. So that is a very interesting. Actually, I put a lot of thought on this and why it happened and something like that. Yeah, it looks very unusual, I would say. And also, clearly we want to compare with the TC and other things to really. I don't know if those small structures can be really matched, but those looks to me as large structures and evolving with time. I believe we can actually talk to haystack people, try to find a case to study this one with maze and compare with TC data. Yeah.
So if there are no other questions, I do actually have one myself.
Yeah.
Do you have a sense, you show a lot of different scale size simulated in these higher resolution simulations. Do you have a sense of what degree the sort of simulation captures what is in reality in terms of like spectrum of waves and their magnitudes?
That's a good question. I haven't really looked into that. I believe Handy did as a kind of a spectrum analysis which the wave power at different wave minor the frequency or whatever, or wave number. So we haven't really looked at it. I don't think we look at it in the maze frame to see what kind of spatial structures being resolved or not resolved, and to how high or how small scale we resolve. I don't think we have done that yet, but that's clearly a topic to need to be studied.
Okay, thanks. And Masumi had a quick question on this slide. She was wondering about the color scale changing, and rather than just keeping it fixed sort of during the whole time period.
Yeah, this one is actually the reason for that is clearly with a storm evolving was that we have a very strong negative and positive storm. The scale changed a lot. So I believe Kevin did this, try to make sure that so we can see the detailed structure. If we use a fixed scale, it's somewhat just, I believe this density is pretty low. You won't see anything at all. So it's that's the big consideration. But I believe if we use logarithm scale, we probably can also see this, not use the linear scale, but really Kevin, I just asked Kevin the last week or something like that, so it's a pretty quick look. So yeah, that's good. Says we probably will, I believe, use the log scale to better resolve those different changes of the electron density with time, rather than a linear scale. So that's
All right, thanks. Are there any other questions? It appears not. So thanks again, Wenbin, for a nice talk and showing the very fresh results.
yeah. Thank you.